Okay, so yes, this is a team effort in Angela's Benedetti team at ECMWF. I'd like to acknowledge my colleagues, Tobias and Samuel Quesada-Ruiz, and also many colleagues at ECMWF and outside ECMWF, in particular from the EUMETSAT and WP staff satellite application facility on collaboration on RTTOF, so colleagues from Met Office, DWD, Meteo France, and acknowledge funding through several projects that help with this development. So a bit of motivation why you are looking at visible reflectances. So satellite observation make a major contribution to the Earth system data, which are routinely assimilated into NWP models. So you have more than 100 million of observations that are ingested daily to determine the initial condition for weather forecast. And at ECMWF, you had long led the way in assimilating humidity, cloud, and precipitation-sensitive microwave data for NWP. And these days, efforts are continuing to exploit the information in all sky conditions, and the aiming is to extend this to a broad range of available sensors, including passive infrared and also active satellite instruments. And you did hear today from COSO and others about efforts in the infrared part of the spectrum and the microwave part of the spectrum. And you would also like to focus here on visible observation that can also provide complementary information to that on microwave and infrared. So in this presentation, you mainly highlights the ECMWF development to exploit visible radiance satellite observation for NWP. So just to motivate this work, I'd like to start with this very nice overlay of the two pictures. One that is coming from first television picture from space on US TIROS-1 satellite on April 1960. And the first visible image in 2017 taken by Ahi on Himawari 9. And this collage is illustrating 60 years of evolution on visible observation. So you can see on the left that in 1960 you had a snapshot of the large-scale clouds, while in present days you have much more detailed, high spatial and temporal resolution from current imagers. However, this data was largely underused in NWP, and we would like to change things in this direction. So for this seminars, we will establish the following objectives and goals, and hopefully by the end of it, we will be able to answer some of them. So we'd like to discuss how we are exploiting the visible part of the infrared, visible part of the spectrum at ECMWF. What are the developments that are required to enable the visible reflectance assimilation? What is the preliminary impact that has been seen in our system, and then future direction for assimilation in our system? So after introduction and preparing the ground, I will present some results of monitoring of cloud visible reflectances, and then first assimilation results, and we'll finish by summary and outlook. So introduction, why can you now attempt to assimilate visible observation? What changed, and why this has not possible up to now? So developments in three major areas has made this possible. First of all, continuous effort in improving the accuracy and the speed of the forward observation operator. So until recently, the cost was too expensive and prohibited the use of RTTOF for numerical weather prediction operational application in the visible part of the spectrum. The second area of development, we know that the data assimilation can only assimilate what the model can simulate. So you need high resolution models, and you need a certain degree of realism in modeling clouds and especially cloud positions. And today you have a high resolution model that can do that. And the last point I want to make is, in particular in the 4D VAR framework, the exploitation of moist linearized physics. So the developments in the TL and the AD that allow forecast to adjust to the cloud observation during the 4D VAR minimization. And here is a snapshot of the electromagnetic spectrum. You did hear about IR and microwave that are used in our system. And the zoom is into the visible part of the spectrum. We are working now in frequency that ranging between 300 and 800 nanometers. So in this presentation, the focus will be on single channel, 655 nanometer, but we are also very much interested on the near infrared part of the spectrum with ranging between 800 and 2500 nanometers, and efforts will continue in these areas too. So what are the observations that are available for visible? We are looking into exploiting both LEO and GEO satellites. So initial focus was on visible reflectances from OLCI on Sentinel-3A and B. OLCI is the ocean and land color instrument, which measure the reflectance of sunlight from Earth's surface and atmosphere in 21 spectral bands at a very high resolution of 300 meters. It's a 10 a.m. Morning satellite with two satellites that are 50 minutes apart. You achieve daily global coverage of all visible reflectances, and this is illustrated here, a snapshot in a particular day in 31st of January this year. Single channel weekly absorb channel at 0.6 microns. And the second set of observations that we would like to exploit are the observation from geostationary imagers in the visible channels. These are level 1.5 observations that are used here. Currently, you are only using product from the geostationary imagers in the infrared part of the spectrum. And in the future, we would like to exploit high-resolution visible reflectances that can offer much detailed cloud information at much higher spatial and temporal resolution than the microwave observation you have in our system. And on the left, it's a snapshot of the available channels per instrument, starting with Seville on Meteosat, ABI in GOES, AHI in Himawari satellite, and the new FCI on Meteosat 12. So you can have up to 8 channels, and the focus initially will be only on the channels in the red part of the visible spectrum. So you need to pre-process and handle the data, and buffer it's the local format at ECMWF for NWP application, and it was required to acquire this data and pre-process in a local buffer. We'd like to thank here to our colleagues in the forecast department for all their hard work on pre-processing and converting from radiances to reflectances, doing all the initial checks and angle calculation, and preparing a buffer template that will enable the near real-time monitoring. So for all LEOs and GEO satellites, you are acquiring the level 1, level 1.5 data, which came in different format, NetCDF or HREAD, and then this is it's converted to a local unified buffer format. Then develop capabilities and build a bespoke data flow to process these visible radiances that are obtained from EUMETCAST. So having the data in buffer, it's very handy for us, but then the data it's super ob. into a Gaussian grid, and considerants here are based on the 4D VAR outer loop resolution. So you have some flexibility on how to do this super robe. You can consider a resolution at 40 or 80 kilometer. This is quite useful. The super robbing is calculating an average of 4 reflectances within a grid box. It's also reducing the representativeness errors and is beating down the instrument noise, as well as reducing the data volume. And the last step in this bespoke pre-processing flow is conversion from buffer to ODB, where the ODB is the in-house data storage software which allow the 4D VAR system to store and access the data. So these are some manipulations that are done into the IFS in order to prepare the data for assimilation. Then you should simulate these visible radiances, and I already mentioned some challenges in the radiative transfer and development that were made in this area that were crucial on developing and allowing assimilation and monitoring of visible reflectances. So first of all, visible radiance it's quite different from the infrared and microwave. This originates directly from sunlight, and it's modelized by a complex radiative transfer. And schematic here it's the radiative transfer equation, where the radiance which is measured by a satellite at a certain frequency depend on our description of the atmosphere, which is done via a Planck term, which depend on the temperature, and this is modeled by the absorption in the atmosphere. But also some other terms are playing an important role here: surface emission, reflection, scattering. And some of these terms are more important in certain parts of the electromagnetic spectrum, certain are in the other one. So, for example, important in visible are reflection and multiple scattering, which dominate the radiative transfer computation and increase the cost of the observation operator. And the way that the visible radiation is reflected and scattered, it's highly sensitive to the detail of the atmospheric constituents, and in particular cloud and aerosol particles. So you also need for accurate surface reflectivity models for land and ocean surfaces. And while the first term is not important for the visible, this is not requiring the weighting function in the visible. You almost have negligible emission and absorption. So in ArctiTOV, which is the observation operator for radiance data assimilation, you have now a cloud visible observation operator integrated. This is emphasis cloud. Emphasis standing for Method for Fast Satellite Image Synthesis, and this was developed by Leonard Czech. And this was crucial to enable the application in NWP in the visible. This emphasis is a fast and accurate approximation of 1D radiative transfer model discrete ordinate method, and it's suitable for data assimilation and model evaluation. The first version was based on lookup table. However, more recently, this was replaced by neural network approach, and this is in ArctiTOV 13.2 and later version. So LUT will be discontinued with ArctiTOV 14. So IFS and WP model fields and atmospheric profiles and surface parameters are the input to ArctiTOV emphasis and N to produce the model equivalent of the observation and compare with the observation. So there are the solution of the radiative transfer. It's based on this neural network approach, and the input layer consists on very limited input parameters. There are now 16 parameters in RTTop 14, slightly more than in previous versions. So emphasis also include TL and AD version. It's used for all solar channels from 0.4 to 225 microns. And at this moment deals with cloud and aerosol separately, and developments in this area are continuing. So once you have the observation that are super Rob and the equivalent of the observation in the age in the model space, you can start looking at the monitoring of cloud visible reflectances. So you monitor the observation, again, state of the art of the NWP model, and this is crucial to see the reliability of both satellite observation as well as model performance. And I'll show an example with Olchi observation. So on the left, it's an average departure map of observation minus background for 3 months period, showing some large biases over certain areas. While on the right is a reflectance histogram showing Olchi observation as well as the first guess. So first look into these results illustrate the need for careful data screening, especially for areas which are affected by ice and by snow, or as the extreme sun or satellite angles. So quality control decisions should be put in place in order to do a better job. And once you are screening for these quantities, CIs, solar, satellite zenith angles, angling, orography removed, you can see that the departures are much more reduced. In this plot, there is still some coastal snow ice, which is showing in both the map and the reflectance, around 0.3 reflectance here. And this suggests that you have to do a better job if you want to remove the coastal snow ice areas. However, if you are focusing only on the homogeneous ocean surfaces, you can see that the departures are much reduced, and this is a very good agreement between the Olchi and the IFS. And in the same time, you can also find some model biases that are known from these departures, as it's shown here in the left figure, over the Pacific on the maritime stratocumulus areas, which is a known bias in the IFS. So we are looking also at time series of daily mean first guess departure and looking this individually for Olchi on 3A and 3B. And it's very nice to see that these results confirm a known observation reflectance bias, about 1% between the Olchi in S3A and S3B. You can see here that there is a drift in this long time series over 3 months, which mainly originate from seasonal variations. And there are changes in Olchi coverage over snow, ice, and vegetation. And a more careful look into these biases is needed to see the dependencies in function of different surface type or satellite angle geometries. And if you are looking here to identify the biases only over sea, you can see that these are much smaller than biases over land. And over land, you can have some problems that are originating from insufficient modelization related to subgrid cloud or cloud overlap assumption that had to be followed up more. So similar with the work on LEO satellite, we would like to extend this to imager data from GEOS operational satellite, the GEO ring. And in this context, you started a joint evaluation and intercomparison of global ICON and IFS model cloud fields. and this was performed during 1 month in 2024. And this is a snapshot of the O-B monthly departure that were obtained using the icon on the top row and the IFS in the bottom row. So the setup for this intercomparison was established together with our colleagues at DWD to minimize these differences, and it's hoped that this study aim to disentangle the observation and the model biases. A poster has been presented at the workshop on data assimilation in early April by our colleagues at DWD. So the very first conclusion are very promising, and you can see that the O-B differences are consistent for all the geostationary satellites, and they are consistent in between the two models. There might be some larger biases remaining or observed, in particular over land in the northern regions. And in this context, you are also looking into using a more dedicated BRDF atlas, which was prepared for this evaluation for January 2024 and was based on MODIS collection 6. So this was a courtesy of our colleagues from NWP staff. And important other parameters are calibration, that has to be a reliable calibration of this sensor. You had a look into severity calibration based on the latest results from EUMETSAT, and the work on this area is continuing. This is reaching pre-operational maturity, where you can start looking systematically at the departures in between the observation minus first guess, and scrutinize more the biases. So you have to mention that at this stage, no bias correction was applied to these observations, and more work is needed if you want to account for a variational bias correction for this data type. I will move now into the very first results with cloud visible reflectance assimilation. So this was based on all the positive results seen from the monitoring experimentation. And as a few remarks here, I would like to mention that this is the very first time that the IFS is seeing visible observation. And these results that I'm showing here today are based on a very suboptimal setup, which was mainly put in place to test that the assimilation it's working. And you have suboptimal screening. VarQC is not yet accounted for. As mentioned, no bias correction was yet put in place, and we didn't do anything for the observation error tuning at this stage. But we would like to illustrate the potential impact of visible assimilation in two situations. Impact on low clouds first, so potential impact of visible reflectance assimilation on low clouds. So this is a very recent situation in April this year, where all observation over Black Sea show a presence of cloud, but it was the cloud was missing in the IFS over this area. So we wanted to see if introducing Olch observation into the IFS can help with the lack of low clouds in the system. So you perform two high-resolution experiments. One is the control as operations, and one in which the Olch observation was assimilated at 50 kilometer super-ob. And you can see that from this snapshot, here you have the IFS first guest on the left, which is missing the cloud over Black Sea. Olchi observation, we have the cloud. And when the Olchi observation are introduced into the analysis, you can see that this help with the cloud formation over this area. So by adding clouds in the Black Sea. In order to show if this is a good or a bad impact and how this is improved, I present here 3 panels. On the left is the first guest departure. The red spots indicate that you have too few clouds in the IFS. And then as a measure of improvement, we are looking at the departure reduction between the analysis departure and first guest departures. And you can see the green regions are regions where the analysis departure is smaller than first guest departure, so it's improved cloud analysis, while the pink is degraded cloud analysis. And same, the increment, the analysis increment that is made by this visible observation show increasing reflectance or adding clouds by using the Olchi observation into the system. In addition of Olchi observation, you can also have the GEOS data from Meteosat 9, which is covering this area. And in addition, Meteosat 9 also offer a much frequent observation, as you can use hourly data. And if you are using Meteosat 9 observation also into the system, you can see that you are improving the first guess, which is it's very nice to see this improvement in short range forecast of low cloud. So there is potential of this data, and for this study, you also look at the impact of other observations that are present in our system, and we are looking at the impact on AMS-2A channel 1 to 5, which seems to improve at first guess. This is assimilated in all sky conditions, and slight improvement in the humidity in ATMS channel 18 to 2022. So work continue in this direction. This is only a case study, which is showing the potential of improving low clouds. But we are also looking into some systematic statistics comparing the change from first guess to analysis when introducing the Olchi data to our system. And you can see that the analysis, it's slightly reduced. The assimilation of Olchi observation reduced the discrepancies between the observation and the model. And this has been seen for 2 different periods, once over September 2021.
Yes, sorry to interrupt. I just wanted to give the 2-minute warning.
Yes, yeah, okay. The other example is the potential of visible assimilation for improving future reanalysis product. So the data is available on geostationary imager, and this go back until the 1960s, 70s. You saw from the very first image the broadband visible observation available in the 60s. And these instruments are supported now in the radiative transfer. So we wanted to see what's happened if you are simulating the reanalysis context like in 1960, and you only have a depleted observing system where you assimilate conventional data, and then you add the visible data from Olchi on top of that. And as shown here, you can see that the analysis departure are much reduced when you are benefiting from the Olchi observation. So the very first results in a depleting observing system show an impact on model analysis and also on forecast. You've seen an impact on temperature and humidity, but also in wind. And here is the reduction in the standard deviation of error in the experiment that is seeing the Olchi observation and a control that is not seeing the Olchi observation. And the improvements are very significant, especially over southern hemisphere, where you have less conventional observations. So we believe that this data has potential not only for NWP application, but also for future reanalysis product. So to conclude, I would like to stress out that technical developments are now in place to allow monitoring and assimilation of all sky visible. You show some results on the monitoring of visible radiances in the IFS. This is reaching now a mature stage for operational implementation in the next cycle. And you also experimented with all sky visible assimilation in the IFS, and we hope to follow on DWD steps as they are already assimilating visible reflectances from geosatellite in the regional model. There is some work to be continued. You identified some biases that has to be addressed in terms of biases. These are smaller over ocean than over land. And the preliminary results from assimilation experiment show some potential for both NWP and reanalysis. And then there is more work to be done in order to have a better impact in the analysis. And all the elements that were mentioned also by my colleagues this morning, variational bias correction, quality control, observation error tuning are all important in order to gain some impact from this data. So if you are interested on this work, some results will be summarized in the upcoming newsletter in summer 2025. And I would like to close here. I added also some references from work that has been used in the literature review. And I would like to close here. Thank you very much for attending this. And yes, I'm asking any question if they are. Thank you.
Thank you. We do indeed have some questions, starting up with Prashant Kumar. Does using more than one visible channel provide any additional important information?
Yes, so at this stage you only experimented with single channel 0.6. However, in the monitoring, you have planned to look at also other channels that are well supported in the radiative transfer and emphasis. For the assimilation, this will be more complex because you have to account for correlation in between these channels, and it's more work to be done. So I think you have to start using more than one channel and then seeing the benefit or the additional complication that have to be accounted for in order to obtain more benefit.
Okay, thank you. Then the next question from Kozo Okamoto. How do you provide effective particle radii and aerosols to RT-TOF emphasis? Are they provided in IFS or are they diagnosed results?
No, these are the aerosol, or this is about cloud. Yeah, these are coming from RT-TOF at this stage, but there are plans to look into that by my colleagues and look at the impact of that into the IFS when this is not from the RT-TOF, but it is from the model.
Okay, so then another question from Shabazz. How can we handle spatial gaps while performing data assimilation?
Spatial gaps?
Yes, I'm not quite
Okay,
sure
so
what.
I think, yeah, all sky is assimilating data in all sky condition. It's one way to mitigate gaps that are seen when data is used, for example, in clear sky condition. Yeah, there are challenges, however, of different surface type and you have to start maybe with ocean, land, and sea ice, and you have to improve in our modeling, on accounting, on radiative transfer computations to be as accurate as possible, and also screen the data, which is not good. Yes, to have a full coverage. I'm not sure if I understand the question, but yeah.
Yeah, I think that suffices. Okay, so then we're almost out of time. I would abuse my power as chair to ask a final question. So do you have almost the same wavelength from all these different satellite sensors, which are almost exact wavelengths? Do you have to account for the differences between those wavelengths they measure, or is that so small it doesn't matter?
This is accounted in the radiative transfer on the RT coefficient computation. So the spectral response function of each of these, it's accounted for. And you can see differences. For example, if you compare the same not the same sensor, but Meteosat 10 Seviri with FCI, for example, which have the same location, and they have both the 0.6 channel there. There are some differences in the spectral response function, and this is not only in the visible, but also in the infrared and results. You have to be mindful of that when you're interpreting our results.
Okay, thank you.